Hi, this is Benny. I've dedicated my life to understanding the universe in hopes that someday I am given the opportunity to hop on a rocket and see it for myself. Growing up, my safe space was between the covers of a book. My friends were people like Percy Jackson, Alex Rider, Paddington Bear, Beatrice Pryor, Hermione Granger, and the Astrosaurs, a group of crime-fighting dinosaurs in space. And so, using Space Bites, this podcast, I am hoping to create the same type of safe space where knowledge is for everyone and anything is possible. Together, we can marvel at the boundless beauty of the universe and find hope within the delicate intricacies that weave the fabric of our world. If there's one thing we have in common as human beings, it is our curiosity, and a curious mind is a happy one. Together, we will learn how the gold in our rings was made inside of stars, how the flap of butterfly wings can cause an earthquake, how charged particles from the sun interact with Earth's magnetic field to paint the sky with glowing lights, and how math is the language that describes everything. Every atom in your body was created in a star. The carbon in your DNA, the oxygen you breathe, the calcium in your bones, all of it originated in stellar furnaces. This means that quite literally, the universe is in you. You are a product of cosmic alchemy, billions of years in the making. The same processes that formed galaxies also formed you, linking your existence to the vastness of the universe.
Oh, so not only is it emitting particles or evaporating, that rate of evaporation increases.
Yes.
Oh, I love physics! Hello everyone, and welcome back to another episode of Space Bites with Benny. It's me, Benny, your favorite nerd. So the Cosmic Conversation segment is about shining a light on the people who are diverse in their ambitions, mainly astrophysicists, cosmologists, and engineers who are more than what they seem to be. And I would say that today's guest encapsulates that pretty well. And so joining me today for episode 2 in Cosmic Conversations is Bertrand Delgado, a fellow astroparticle physics student at ETH Zurich. Raphael and I recently joined the same research group, and upon having a couple conversations, I realized he would be a perfect candidate for the Cosmic Conversations segment. Hi, Raphael.
Hello, Banan. Thank you very much for inviting me today.
Yeah, it's a pleasure. So can you tell me a little bit about yourself?
Yeah, sure. So maybe I can give you an idea of what I did the last years. So I started my bachelor's in physics at EPFL Lausanne in 2019. I did my 2 first years there, and for my third year, I had the opportunity to be selected for a year abroad at Imperial College London. And so therefore, my bachelor's thesis worked on magnetohydrodynamics, so plasmas in low Earth orbit, and also their effects on satellites. So that was in 2020, finished in 2022. And then I decided to take a break from physics, and so I went back to Honduras, Central America, and started working on what I like. So I started a bachelor in modern literature that I hope to finish one day. And well, I've been working on photography, so I've had like several black and white projects, mainly when I was trying to sort of capture the beauty of the routine in Central America, on the coast or also inlands. And I also shot a film, which is called 35 milímetros más tarde, so 35 millimeters later.
Wait, and what's the short film about?
So, as it is indicated in the name, it's sort of a tribute to analog photography. So these 35 millimeters format photography, and it's the story of an old photographer that lives in the coast, on the Honduran coast, the Caribbean coast, and he always wanted his art to be recognized. However, well, he lives from his wage as a cook and mainly from the money that sends his daughter in the US, and he lives with his grandson, but their relationship is pretty cold, let's say. Actually, much colder than cold. And yeah, just one morning, he takes photos of the sea, and then he goes and develops these photos in his darkroom, his actually bathroom that he turned into a darkroom. He sees something weird in the negative, and he believes that he's got the only proof of a murder. So then there's a whole conversation between him and a journalist friend about, well, the value of art, the value of journalism, truth, and then also other topics that are discussed in the film. But I guess you have to watch it.
That's very interesting. Yeah, well, you don't want to spoil too much because you don't want people to end up watching this short film that you made, right?
And so this also, well, at the same time during this year in Honduras, I continued working on plasmas in low Earth orbit. So actually, I pursued my research as part of the Morazán project, which was a project in the Universidad Nacional Autónoma de Honduras, so National Autonomous University of Honduras, which was, well, which planned to send a CubeSat, and so like they were interested in the effects of plasma on such a CubeSat, depending on the latitude and the orbit. And so we worked on a paper with Ravindra Desai and Fernando Sorto that was published and presented at the International Astronautical Congress in 2023 in Baku.
Baku, Azerbaijan.
Exactly, yeah. And so that was the year 2022-2023, and then I went back to studies in fall 2023. So I arrived in Zurich, started my master's at ETH, and here I am now.
And so you started your master's research with Professor Sori Santos, and this is how we met because we're in the same research group.
Precisely, yes.
So today's episode is about general relativity, and it's a very broad topic, and we're going to try to talk about as many of these interesting things as possible. I would say general relativity is kind of like this whole new branch of physics that I started only studying now, and it really has shown me that our knowledge of physics is very, very shallow. The more that I study, like the more that I learn, the more I realize we really don't know that much. So do you want to start us off on this journey into general relativity?
Okay, all right, let's get started. Maybe before introducing general relativity, we could talk a bit about special relativity. So maybe the main thing about special relativity is that laws of physics are the same for observers that are in the same inertial frame. And so you've got this idea of time dilation and length contraction and dilation as well in special relativity. So because of that, observers might disagree, for example, on the order of events. So for some observer it could be simultaneous. For another one it could be like one could happen before the other. But they would agree on causality. So causality is the fact that in special relativity, when you consider a point in your special relativity space, you've got what we call a future and a past light cone. And so what is inside your future light cone could be any consequence of the point that you're considering. So the point could be the cause of it.
So something happens in the past or in the present, and that has a direct effect on the future.
Exactly. So it could have an effect. It could have any effect on your future light cone and your past light cone. That means that any point in the past light cone could be a cause of the point that you're studying now. Any curve that joins two points that are in this, so one that is in the center and the other one in the future or past light cone, would be what we call a time-like curve, because they could be related. Outside the cone, we would have something that is called a space-like curve, because they would be causally disconnected. One cannot be the cause of the other. And then what is on the edge of the cone, on the light cone, it would be a light-like curve. So that could only be connected by light, because you would need to travel at the speed of light, which is the upper limit of speed, in order to reach this point. Yep.
So in very simple terms, just for people listening that might not be familiar with these terms, is it okay to say that special relativity is when we were talking about things that are traveling at the speed of light, and general relativity is for things that are very, very, very heavy?
So, special relativity introduces the idea of relativity, of causality, and the fact that we use a four-dimensional space-time. And so we include time in our coordinates. And then the idea of general relativity, as you said, is that we'll include gravity and therefore will actually bend our space-time. And that's when it gets... I mean, it's already very interesting when we talk about special relativity, but then when we go up to general relativity, it's even more interesting. So yeah, there's this there's this idea. So I talked about coordinates, and we've got this idea of proper time. So imagine when you draw axes on a blackboard, usually you can use a two-dimensional space-time, and you can set a grid on your board in order to define your coordinates. So the origin 0, 0, 1, 1, 2, 1, etc. Now you can imagine also a three-dimensional grid around you. And the idea would be to have a four-dimensional grid. So we would include time as well. So here, with our poor brains that live in three spatial dimensions, it's quite hard, if not impossible, to imagine. But maybe, what I like to imagine is a three-dimensional grid, and on each node, a clock. And so, the clock would be ticking differently on each node.
Yeah, I was about to say, that's how I would imagine it. A three-dimensional object, going from a two-dimensional object, a square, into a cube, and then a cube that has, like you said, these individual clocks to measure time, and that would be four-dimensional space-time.
Exactly. The only difference here is that the signature of the metric, so I'll talk in a bit of what the metric is not the same as what we have in Euclidean space. So, in Euclidean space, if you want to calculate a distance in a flat space, well, you just sum up the squared of the coordinate, and then you set a square root. So if I want to know the distance between me and the building over there, I do x squared plus y squared plus, if also the altitude is different, z squared, and I put a square root on everything, and I've got my distance. Here, if we want to calculate the distance in 4 dimensions, in special relativity, we would use the sum of distance squared minus the time squared. So we've got this minus plus signatures, plus for the space coordinates, minus for the time, or reverse depending on the convention, in order to calculate this proper time.
Is that why the Minkowski matrix has a negative symbol for time and then positive for the spatial coordinates?
Exactly. So that's the difference. So if you just take the spatial coordinates of your Minkowski matrix, so the +1, what you have is a flat Euclidean space, and you merge into space-time, and you include this minus ones in order to also include time. And the importance of this signature is the idea of causality, that you've got a minus here. So if your proper time when you calculate it is equal to 0, that means that it's actually what light travels. So it's the light proper time. If it's something positive, it's what we called before, depending once again on the convention. But if it's something positive, it would be a time-like curve. That means that two objects that are separated by this 4-dimensional distance can be causally connected, and if it's negative, then it's a space-like curve and they cannot be connected.
Wow, that's a very good way of putting it.
And so therefore, these coordinates that we talked about, so on your 3-dimensional grid, then we set it in a 4-dimensional one, is what we call the metric. And the metric becomes very important in general relativity. About the signature and the metric, that's why we call it the standard one, a 1+3 metric, because we have 1 dimension of time,
and 3 dimensions of space.
Exactly. And the difference is that just our time dimension, so far as we can see, goes forward, and it's the only difference with our 3-dimensional spaces. But maybe later, if we've got time, when we'll talk about gravitational waves, we could also talk about what we call 2+2 metrics.
That sounds very interesting. I don't think I've heard of that one before. Maybe in this semester's modules. So what really intrigues me about general relativity is our approach to gravity. So all along, for all these years, Newton had his theories of gravitational forces. And I know that Einstein came along and was like, okay, maybe we can think of gravity as something different, right? And that really, really intrigues me. So can you kind of tell me a little bit about that?
Yeah, sure. So historically, at the beginning of the 20th century, there was this first, what motivated general relativity were some problems that were not resolved by Newton's theory.
Problems like.
One of them, and the main motivation was the precession of Mercury's perihelion. So Mercury orbits the Sun, and it's got a ellipsoidal orbit, but this ellipsis shifts, and this shift was not, the exact shift was not predicted by Newton's theory of gravity, and therefore that was one of the motivations.
So just explain, because, of course I understand, I'm also a physicist, but for the people that are not familiar with this, what is the problem with that? Why is it an issue that this ellipse is shifting as Mercury orbits around the Sun? What does that tell us?
Okay, just the ellipse is shifting. This is predicted by GR. As you've got in the center, you can calculate it if you've got a rotating object, a rotating mass in the center. This would induce a certain rotation of your movement around it. And actually, it's quite interesting. Fun fact about this: 50 years ish before general relativity, so second half of the 19th century. Neptune was discovered because of some variation in Uranus orbit.
Oh, so they discovered Neptune because it was obvious that something was affecting Uranus's orbit.
Exactly, and so it was affecting it, and so some guy named Leverrier did the calculation, and he expected to find a planet. Okay, right there, that's where we should find the 8th planet because of this discrepancies in Uranus's orbit. And actually, Neptune was exactly found there. So then, when they learned about this problem of Mercury's perihelion, Leverrier came back and he was, hey, I'm going to do the calculations again. I told you so.
Yeah.
And so he came up with the idea that actually, so he was not putting in question Newton's law, and that there would be a second planet on the other side of the Sun that we couldn't see.
Which planet?
I think it was Vulcanus, something like this. Vulcan, yeah. But I mean, this planet doesn't exist. But his idea was that Mercury's perihelion precession would come from a 9th planet that would be on the other side. So he just used, because he had been very successful with the discovery of Neptune.
He got cocky.
Yeah, exactly. He was, I'm not gonna discover another planet now. Watch me. And sorry, all my respect to this to this scientist, but actually that wasn't the case, and the idea was actually Einstein's general relativity. Also, another motivation for it, not only this problem, but the fact that also half a century before, Maxwell came up with his theory of electromagnetism.
Wait, but you still haven't told us what general relativity is. You talked about all these motivations.
I'm talking about the motivations, and then we can go into the hard stuff.
Interesting stuff, not hard stuff.
Yeah, interesting stuff. And so Maxwell really had this idea of fields, the electromagnetic field. And so also one of the motivations was to set gravity as a field force. Have a field description of gravity. That was the other motivation.
What does that mean, to have a field description of gravity?
Let's talk about this. So to introduce this, so we're gonna talk about fields and all that, but I think that importantly, the first idea of Einstein was this change of paradigm that, as you're saying, that gravity is not a force, but a curvature of a manifold, and that's your field. So
curvature of manifold. Say, what is that in layman terms?
So I think the other day you had actually a very good metaphor. It's like when you think of a trampoline, and for example, you put a marble on your trampoline and you pinch the center. Well, then the marble will start rolling towards the center. So the idea is that here, when we talk about a trampoline, it's a two-dimensional manifold, then we have to think it in 4 dimensions.
So manifold here, you're just saying fabric of space-time.
A fabric, yes.
Yeah, a fabric, yes.
Yeah, definitely. So that's the idea, and also one of the central ideas of general relativity would be that objects are in free fall. But now that gravity is not considered a force, but a curvature of space-time, well, that means that free fall is actually the state where no forces acts on your object. So if you're in free fall, you would follow lines on this curved fabric, on this curved manifold that we call geodesics. So these geodesics are the shortest or the longest path. Mathematically, it's if you've got some knowledge in differential geometry, it's the parallel transport of the tangent vector along your line. And so here, the natural behavior of an object in GR is actually falling. So this is a complete change of idea of paradigm, because if you take, for example, usually when you introduce GR, we use this metaphor. It's not anymore the apple, Newton's apple, that is falling on Earth. Is the Earth that is accelerating towards the apple, because you're studying the apple and the apple is in free fall. So you're in the inertial frame of this apple, and it's the floor that is accelerating towards you.
I love that. Like, every time I hear someone talk about this, it still blows my mind. I just find it incredibly interesting.
Yeah, it is actually interesting. And so, yeah, maybe that's the main pillar of GR is what we call the equivalence principle. The fact that laws of physics are completely equivalent and they're uniform motion. And let's keep in mind maybe as well that it's a different description, a more complete description of gravity. But that doesn't mean that Newton was incorrect. Just like GR is not incorrect, these are effective theories. So that Newton works perfectly on a certain scale. So like on Earth, if you're dropping a ball, for a plane flying, etc., etc.
Effective theories being theories that help us explain why these weird things in our world keep happening. Like you said, the one with the Mercury precession we don't understand, so we can use Einstein's theory of general relativity to explain that.
Yeah, an effective theory in the sense that it works in a certain at a certain level of space, of distances, time, and energies, but then it could fail at another one. And for example, general relativity is not a complete theory.
It only works on large scales, but it fails on smaller ones.
Exactly, on very, very small scales, so below the Planck length, or on very high energy scales, so above Planck energy. Here, there's this whole question of quantum gravity, and we struggle to actually to have a quantum description of gravity above these energies. So once again, GR works very well to explain most of the physics that we see, but it's not a complete theory as well. So none of both are incorrect.
Cool. And I know that obviously to encapsulate this theory, Einstein had to come up with an equation that describes all of this, the curvature of space-time, the gravitational effect.
Okay, yeah, definitely. So, yeah, I think it's time to introduce Einstein field equation that describes GR. So it is a beautiful equation. So on one side, you've got the Einstein tensor, G mu nu, and on the other side, yes.
Whoa, you have to go back 200 steps. You're gonna have to explain these different variables in the equation, because the word tensor is not a very well-known word.
Sorry. Okay, so maybe what is a tensor?
What is a tensor?
So a tensor is a mathematical object, and it's an application from one space to another. So what we call from a covariant space to a contravariant space. So these are technical terms, but the idea is that it generalizes the idea of scalar, vector, and matrices. So when you have a scalar, it's just a number.
Magnitude.
Lambda, for example. You've got a vector, that's, for example, in a 2-dimensional or 3 dimensions, you can describe it as an arrow pointing towards a certain direction.
So something that has magnitude and direction.
Exactly.
So it could be a positive or a negative value, not just a number.
Then you can generalize a bit more and have a matrix. So just depending on the rank of your matrix, this is an application, and so you can set vectors and it transports one vector to another vector space. And then, so for example, a vector is a rank 1 tensor. A matrix is a rank 2 tensor. And so the idea is that a tensor could be any rank, and it would be this application from one space to another, taking in argument several vectors or matrices. And also one important thing is that it's got a very particular way of transformation under change of coordinates. So that allows to have a uniform description of our physical phenomena under different observers, because we can change coordinates and our tensors would change accordingly to these coordinates. So yeah, let's consider it as a mathematical object. And so Einstein tensor, the idea is that it encapsulates the curvature of space-time. So we can then break it into other tensors and scalars. But the idea is this, that it's purely curvature. That's on the left side of our equation. So it's G, capital G mu nu. And on the other side, we've got our energy momentum tensor. So we've got a certain factor that we can develop a bit about this later, but let's call it kappa so far, times T mu nu, and T is the energy momentum tensor. So energy and mass, as you know, it's the famous Einstein equation. It's related, it's the same.
E equals mc squared.
Exactly. So any mass or energy is encapsulated in this tensor. And what that means is that if you input any energy, any mass, you would have the curvature on the other side. And if you input any curvature, you would have therefore some energy.
Wow.
And yes, actually, now that I think of it, it's one of the reasons why gravity compared to electromagnetism is highly nonlinear, from the idea that gravity gravitates, so that like any energy momentum tensor would create a curvature, and any curvature would create would be related to energy. So both are intrinsically linked, not like, for example, electromagnetism, where an electric field is not electrically charged. Here you've got that any tensor would bring curvature, and if you've got curvature, you've got a tensor. So that brings nonlinearity. And then talking about this equation, I did not develop the factor that is in front of T mu nu. So this factor is like 8 pi times g, the universal gravitational constant, divided by c to the 4th, if I believe. What is interesting is that we can see here, I mean, it's sort of a hand-wavy argument to say that gravity is very weak and that we need very massive objects to see its consequences, even if now actually we can measure it on very, very tiny objects, but still.
I mean, weak in this, I don't know what sense you mean weak, because if we think about the 4 fundamental forces, you've got the gravitational force, you've got the strong and the weak, and the electromagnetic. The strong and the weak act on very, very small scales. Electromagnetic force is strong, but it kind of cancels itself out. So when you say the gravitational force is weak, relative to what? In comparison to what?
Okay, if we compare it to the other forces, indeed, it is the weakest. The thing is that the others decay at larger scales. So, for example, in our everyday life, we don't see the weak and the strong interaction.
But our atoms do.
Yeah, exactly. The theory of electromagnetism, the electromagnetic interaction also decays with distance. So at the end, we just observe gravity, but actually gravity is the weakest of the four, and the idea is that it is actually very weak, because if you compute numbers, once again it's very hand wavy, but you've got in this equation the gravitational constant that is like 6.67
times 10 to the minus 11.
Exactly, divided by the velocity of light that is 3 times 10 to the 8, so 10 to the 32. So 10 to the minus 7 divided by 10 to the 32 would like 10 to the minus 40. And so we've got a very, very small factor in front of our energy momentum tensor. So you need a tremendous amount of energy to have a visible curvature of space-time.
Do you feel cool saying that? Saying curvature of space-time?
Yeah, I think it sounds good. Why?
I know, I enjoy saying it. I say the curvature of space-time. I just think it's very intense.
Yeah, definitely. So we've got this idea, and therefore with this intrinsic link between gravity and between mass and curvature, we can get to like mind-blowing objects like black holes. The idea is that you've got an object before forming a black hole that is so dense that it cannot counteract its gravitational pull. So therefore the matter of this object is attracted towards the center, and therefore it becomes more dense. And because it's even denser, then it can even less counteract this gravitational pull, and therefore you've got a collapse into what we call a singularity.
And does this process start with a star, or is that not necessary?
It's not necessary, but so the first black holes that I believe that we observed were the first that was directly observed was not a stellar black hole, but yes, it could come from a star. So from the collapse of a star. So at the end of its life, the star has no more fuel to counteract the force of gravity, and it is massive enough, so it collapses. And so some would collapse into a neutron star, and if you overcome the degeneracy pressure of the neutron star, then you collapse into a singularity that is a black hole.
And black holes are really massive, compact objects.
Exactly, but you can also have. Actually, it's a very good question. What is the origin of black holes? Because you've got stellar mass black holes, but you've got more massive black holes like 10 to the 6 solar masses. You've got supermassive black holes in the center of galaxies. Actually, the first one that was directly observed was a supermassive black hole. These are 10 to the 9 solar masses, so just imagine a solar mass is 10 to the 30 kilograms. Mm-hmm. So it's 10 to the 9 times 10, it's 10 to the 39 kilograms is something very heavy.
Insane. You would not want to go to the gym and see that on the scale.
Yeah, exactly. You don't want to squat this weight. And then you've got other sources we can talk about this maybe in the next episode, but primordial black holes seeded by inflation. So these are...
You just said very heavy words there. Primordial black holes and inflation.
Yeah.
Such heavy topics, but yes, sorry, continue.
So black holes are very massive, so they have a very strong gravitational field. And why are they called black holes? Because actually nothing comes out beyond a certain distance. So if you cross what is called the Schwarzschild radius, if you go beyond it, so if you're distance to the singularity is lower than Schwarzschild radius,
you get sucked
that
in.
is like twice the mass time other factors. So you've got a distance, but let's think 2 times the mass. Then you cannot escape it, and that's why no information comes from the black hole, not even light. If light enters and crosses this radius that actually we call the event horizon. I find this word very poetic. The event horizon.
Event horizon. Yeah,
because no event comes beyond this horizon.
Well, thank you for that explanation. But actually, did you know that in Interstellar, their depiction of a black hole was apparently quite accurate, because they had a team of, I think it was astrophysicists, working on this, making this depiction.
Yeah, definitely. It's I think it's a pretty good representation. So what happens is that even if nothing comes out of the black hole, because it's got a very strong gravitational field, you would have matter, gas accreting around, heating up, and therefore emitting some light. So that's what happens. That's what happens around a black hole. Actually, was it like 5 years ago?
They took the first image of a black hole.
The first image of a black hole.
Yes.
Actually, what you see is the accretion disk around this supermassive black hole. So the matter that orbits around and that is heated up. And actually, it's very interesting, because if you look at the picture, or also, for example, in Interstellar, what you've got is that you've got the disk that is that is around the center of the black hole, and then you see also like some sort of the disk above as well. And what you see, or like the light that you see above the black hole, like a crown, is actually what is behind it. But because we're now in a curved space-time and objects follow their geodesic just like photons, well, what happens is that light that is emitted behind the black hole would be deviated and would be seen, would come to us, but actually it was emitted behind it. So that's why we see it as something above it.
Makes sense, because more mass equals to more curvature equals stronger gravitational effects. Black holes are incredibly massive, therefore there is more curvature, therefore that's why you see the light that's supposed to be behind, you see it in front. And in our universe, that makes total sense.
Yes, definitely. So also this is another topic, gravitational lensing, that is very, very interesting. And actually, maybe like a little story about gravitational lensing.
Yes, tell me. I love little stories.
The first time that it was measured and observed, right after Einstein had published his theory of GR. So there was this idea that light could be bent, and therefore we could observe a gravitational lensing. And it was actually observed very early, because there was on one day there was a solar eclipse, and so the sun was hidden by the moon, and you could see therefore in plain day you could see the stars around the sun, because the light of the sun is not bothering anymore. And we have very precise maps of our sky, so we know the exact position of stars. And actually here, when they measured the position of the stars around the sun, they would see that there was a tiny variation with what was expected. So, conclusion of this, the light that was emitted from these stars was deflected by the sun, and therefore the image of the star would have a slight deflection of angle and would be seen like with a slight deviation with what was expected. So actually that was one of the first arguments for GR, in addition to Mercury's perihelion precession. So very, very interesting. But let's go back to black holes. So the interesting thing about black holes is that, we said that nothing escapes it. So you've got interesting physics inside the radius, the Schwarzschild radius of your black hole, And actually, what happens is that when you cross the horizon, every geodesic points towards the singularity.
So when you cross the horizon, every line within this space-time fabric is pointing towards
The singularity.
the singularity.
And yeah.
And the singularity is like a super compact. I don't know if calling it an object, I feel like, is wrong.
Yeah,
Just
it does.
a singularity is what it is. I can't even like. It's just is. Yeah.
But you said it. You said it perfectly. It's like these lines in our four-dimensional space-time that points towards it. So if it were just space, I mean, if you've got an infinite amount of force, you can just escape from from the gravitational pull, and you could escape from the black hole. But the idea is that because you've got your geodesic that points towards the center, we have to take into account time. So maybe we could picture it as if you cross the event horizon, you cannot escape the singularity.
Even if you had an infinite amount of force?
Even if you have an infinite amount of force, because your time geodesic points there, and you cannot escape the singularity just as you cannot escape tomorrow.
You are building up to that. I love when my guest speakers blow my mind like that. That's crazy. Thank you for saying it in such a poetic way.
So we could see it that way, like, I'm sorry, but you and our listeners...
So you don't believe in time travel?
Would
then?
not... yeah, okay, maybe that's another idea, but yeah, no, not really. But like, you can't escape Monday. I'm sorry, but on Monday you'll have to go back to work. Well, if you're on the black hole, you cannot escape the singularity because it's just like your Monday.
Yes.
It'll come at a certain point,
and you can't escape it.
And actually, if you try to put force to induce any force to escape, you actually you'll arrive closer to your to the center, because, as we said, the geodesic is the longest or the shortest path. So if you do not apply any force to your object, for example, to your spacecraft that is inside the black hole, it would just follow the longest time path to the singularity. So if you want to live long enough, as long as possible inside the black hole, do not turn on your motors, your fuel, and just let yourself
If
fall.
they survived, if your engine survived entering,
Yeah.
because what I know is, for example, if you're a person and you somehow find your way in space and you're caught within the Schwarzschild radius and you're inside a black hole, you basically turn to spaghetti.
Yeah, there's this idea of spaghettification, right?
Oh, and they've okay, the ification of spaghetti.
Because if you fall inside the black hole, the gravitational pull on your feet would be much stronger than the one on your head, and therefore you would be just
stretched out,
spaghettified.
Yeah. And I also know that, fun fact, black holes are very compact. Theoretically, they could fit in your pocket.
Yeah, they're point-like.
Yeah.
Well,
like travel-sized Oreos.
Yeah. It's just that here, yeah, it's maybe better to not put it in your pocket. But it is very compact. But you've got this event horizon, this Schwarzschild radius, that is proportional to the mass. So actually, the more matter it absorbs, the bigger it gets.
And you can't talk about black holes without talking about Stephen Hawking.
Yes, indeed. Okay, let's talk about Hawking. So classically, black holes would only grow, and actually, you've got the area laws of Hawking that was, I think, in the early 70s, that was it was postulated and demonstrated by Hawking that the area of a black hole cannot decrease in a classical point of view. So
you mean if it absorbed a bunch of matter and grew in size, it cannot go back to being a small object?
Exactly.
Okay.
And also in the same years, so early 70s, Bekenstein actually found a good analogy between laws of thermodynamics and black hole characteristics, black hole laws. For example, this area law has a direct analogy with the second law of thermodynamics, which is that the entropy of a system cannot decrease. Just like black holes. But it was so far just an analogy until Hawking had the idea of diving into quantum field mechanics. And here he postulated the idea of evaporation, so that black holes would emit particles and therefore evaporate.
So black hole eats a bunch of stuff, black hole gets bigger, black hole also has the ability to evaporate by letting loose all of these particles. Is it the particles that it originally absorbed, or what particles is it evaporating?
Well, for that you have to consider quantum field theory, and the idea is that consider just what we call a Schwarzschild black hole, so a not rotating, not electrically charged black hole.
He really is making our lives hard by naming everything after himself. But yeah.
Actually, okay, little parenthesis about Schwarzschild, because I think that he's an awesome guy. I'll skip a few minutes if you want to go back to Hawking radiation. So in 1915-16, around there, Einstein had his theory of general relativity. And so he presented it at that time, and Schwarzschild was in the army. He was fighting in the Great War, in World War I. And so during time of permission, he was back in Germany, and he went to the Science Academy. I don't remember which city. I don't know if it was Berlin. Sorry for that. And, well, he heard Einstein talking about his theory, and he was amazed. And this guy, in the horror of the trenches of World War I, so just picture like this constant bombing on the trenches, etc., this scientist managed to get the first non-trivial solution of Einstein's equation. Yeah, he managed to have the first solution, which is the Schwarzschild solution, which is considering an isolated object, and he considered a complete different metric, what we call the Schwarzschild metric, and this is what allows to describe a stationary black hole. And at first, Einstein did not even believe that such an object could exist, but it's very interesting because Einstein and Schwarzschild were communicating, sending themselves letters, and Schwarzschild was on the front. He was fighting at the same time, and so they had an awesome. They started writing an awesome paper, and so it was published in 1916, if I believe well, like end of 1916, and a bit before, I think, Schwarzschild died. He was, not on the front, but I think he caught some disease in the trenches, and he died before the publication of his paper. And his paper was the first solution of Einstein's equation, and it's what allowed to describe black holes and, well, in general, just isolated objects in space-time. So if you wanna describe Earth, the Sun, or etc., you can use Schwarzschild metric. So just this guy solved Einstein equations in the trenches.
That's amazing. I didn't know that about him. When you say it like that, I'm like, you know what? That's fine. If he wants to name all of these things after himself, I'm totally cool with that.
It's fine, right? And actually, if my German is correct, it's actually pretty. I don't know if it's a fun fact or it's interesting.
Do you want to take it?
But Schwarzschild means black shield. So he's sort of the father of black holes. And
do you believe in fate?
Yeah.
Do you believe in destiny?
Could have been.
Could have been destiny.
Yeah. All right, so let's go back. Let's jump.
We took a little detour,
yeah, exactly.
but that was really interesting.
So that was early 20th century. Let's go back 60 years later, so in the 70s. And the idea is that Hawking has this idea of had this idea of black hole evaporation. And so, consider in empty space, vacuum around your event horizon, so around your Schwarzschild radius. Vacuum is empty in classical mechanics, but not in quantum field theory. Vacuum is not empty because you can consider it as just inside you've got spontaneous emission of particles and antiparticles that appear and annihilate each other. So you've got actually continuous emission of positive and negative energy. They annihilate each other. So on average, you've got also a constant, a null energy of vacuum.
Cancel these.
Exactly.
Yeah. They cancel each other out. And
but in these, if you consider field theory, you can easily have actually these emission of particles and antiparticles.
So basically, just to recap, a vacuum is, for example, like space. Empty space is a vacuum, and that is why, for example, you can't have sound. Like, there's no sound in space because sound can't travel in a vacuum. I'm just saying all of this to help people understand what a vacuum essentially is.
Yeah. So the vacuum is empty, but not empty. It's empty on average because the energy would be set to zero on average or constant. But you've got fields that interact and therefore can create particles and antiparticles. So vacuum is not nothing.
Because to have nothing, you must first have something.
Right, exactly.
You taught me why.
You've got this, and the idea is that if you create a pair of particle and an antiparticle in a normal quantum field vacuum, yes.
Pair of particle and antiparticle, in the standard model of particle physics, for every particle, you have a corresponding antiparticle with an opposite charge. So, for example, you have an electron and a positron. You have a
quark and an antiquark.
Yeah, that's the cheating answer. I was hoping you'd give me another set of. But anyways, I'm again explaining this, trying to add more context to what you're saying. Yes, continue.
Yeah.
So when you've got these particle and antiparticle pairs, same particle, different charge.
Exactly. So your antiparticle has a negative energy, and because there's something, you've got Heisenberg uncertainty principle. You've got an uncertainty on like the delta t, the amount of time, and the delta energy, and from this you can infer a maximum lifetime of your antiparticle. So therefore, your antiparticle is condemned to be annihilated, right? But what happens if you've got a pair that is created just next to your event horizon, and you've got the antiparticle that actually is created but crosses the horizon, and therefore here it can survive due to because there is a change of signature inside the black hole, just like the signature that we talked about at the beginning in special relativity, the plus minus minus. So you've got like a plus in front of time and minus in front of space, or inversely. Well, here we've got a change of such coordinates. So in your Schwarzschild metric, like if you cross the horizon, your space becomes time, your time becomes space.
Mm-hmm.
Well, and so from this, you've got that your antiparticle can easily survive inside your black hole. So it crosses the horizon.
So you've got this particle and antiparticle, and the particle is outside, but the antiparticle has somehow crossed the threshold into the black hole, and now you're saying that because of its signature, it is able to survive.
Exactly.
Okay, keep going. I'm with you.
And so, okay, let's forget the antiparticle.
I can tell you're about to blow my mind, and I'm so excited for it. Just let's get to the.
So it has entered the horizon, the black hole, and so now our regular particle is still outside and can travel to infinity. So as it travels, it is redshifted, but it can be measured.
Redshifted, as in its wavelength has been stretched towards the red part of the light spectrum.
Exactly. And so that's basically how Hawking radiation works. The idea is that you have to consider a non-empty vacuum, so a QFT, a quantum field theory vacuum.
So a vacuum that has nothing, but technically has something, because to have nothing, you must have something. Yes?
Yes, we could say that. And so it's very interesting because on one side, because your black hole emits particles.
When it evaporates,
when
unquote.
When it evaporates, we'll say later why also it evaporates. But therefore, it emits particles, and from it could be considered as a black body. Black body. Careful, not like black hole, but from Stefan Boltzmann law that says that if you've got emission of radiation, that means that your body has a certain temperature. Actually, your power of radiation is proportional to your temperature to the fourth. And so, from this particle emission, we can infer temperature on your black hole, and this temperature is intrinsically linked to your black hole properties, what we call surface gravity. And hence, with this, you can actually do a link between laws of thermodynamics and black holes' laws. And it's not just an analogy, but there is an intrinsic link, because actually black holes have a temperature, so they behave as thermodynamic objects. And funny enough, and Bekenstein had this idea of black holes satisfy laws of thermodynamics. They should not break them. Hawking was a bit skeptical with this idea, but then he had this description of emission of black hole emission, and he was actually. Bekenstein is right, and black holes satisfy laws of thermodynamics. And that's in one of his papers that I told you about that he called black hole explosions.
Question mark?
Yeah, question
black
mark.
hole explosions.
So yes, and on the other side, your black hole evaporates because it absorbs negative energy particles.
Negative energy particles, because one particle is able to travel freely while the antiparticle cross the threshold into the black hole.
Yeah.
And antiparticles generally have negative energy. That's why you're saying negative energy.
Exactly.
Particles,
So it absorbs negative energy particles, energy being mass, negative mass, so the mass decreases, so evaporation.
What? That was what?
Yeah. And
so when they initially said that the area of a black hole could not decrease, they were wrong.
So in the classical sense, no, if you consider like classical mechanics, but yeah, indeed, when you go to quantum field theory, the area can decrease
because you've got a particle with negative charge, therefore negative mass.
Yeah, from emissions. But actually, and also that is interesting. The temperature of the black hole, is proportional to 1 over the mass, which means that the higher the mass, so the more massive the black hole, the lower the temperature. So the lower the temperature, the less emissions you have. So in consequence, a very large black hole, so a stellar mass black hole, or even larger black holes, but regular black holes that we find in astrophysics, are large enough to have a very small radiation, and actually they do not decrease because, for example, they absorb CMB photons, so from the cosmic microwave background, that is this background that emits photons almost isotropically.
That was released 380,000 years after the Big Bang.
Precisely, yes. And so, therefore, they absorb more energy than they emit, so they don't decrease in size. But if you've got a very small black hole, we have not observed yet, but we could observe Hawking radiation, and also the big question is what happens at the end when the black hole emits everything. Also, as it emits, it loses energy, it loses mass, and therefore it emits more.
Oh, so not only is it emitting particles or evaporating, that rate of evaporation increases.
Yes.
I love physics.
Because maybe you could see it as a large black hole would have a very large Schwarzschild radius, and therefore the space-time around it would be just mildly curved. So you would have less Hawking emission. But if you go to very small black holes, you've got a very small radius, and therefore, your space-time it's much more curved. And here you've got a it's a very qualitative picture, but you would have more emissions. And then what comes after? So this famous question: black hole explosions?
Question mark.
And yes, basically that's about it about black hole radiations.
Wow. Thank you so much. That was very interesting. As you could tell, I was very excited about all that information that you had. But I think that's all that we have time for today. So I hope you enjoyed being on Space Bites with Benny, and thank you for being our second guest speaker on Cosmic Conversations. If you enjoyed this episode, please follow and hit the bell button so that you get a notification every time I post a new episode. And thank you for listening.
Thank you very much for listening, and thank you, Benan, for inviting me.